Hello, everyone. I'm happy to see so many people here today, and I hope you will enjoy my presentation. But before I start, I just want to make a very clear statement that everything what I'm going to tell here has nothing to do with my employer and just my personal research. And even some opinion might reflect the same view as my employer's view. It's not the same. I'm here as an independent researcher trying to present my own Moonlight project. So, okay, what I'm going to talk about here today. Today's topic is LKRG under the hood. And I will try to present a project which I fully designed and developed in my spare time, which is currently defended by OpenWall, which is cool. And I would like to give you a better understanding what this project is, tell a bit more about some decision which I made, talk about internals, why some decision was made in this way, not in another way. Also, in the end of the presentation, maybe I will have some time to talk a bit about the future of this project, and we'll have maybe some time for question and discussion. But before I start, just 2 sentences about myself. My name is Zabrocki. Sometimes I use nickname pi3 among others. Currently I work at Microsoft in offensive security research team under David Weston. In the past I used to work for European Organization for Nuclear Research, known as CERN, Wrocław Center of Supercomputing, HISPA Systemas, known from the VirusTotal project, and Sigital, and a few more. And on my free time, I also do bug hunting, and I found vulnerabilities, among others, in the Hyper-V hypervisor, in OpenSSH, on GCC SSP Propolis implementation, in Apache, XPDF, and few more, which I have CV numbers for. I also like to study exploitation techniques and the way how to bypass some modern mitigation, how to improve them, and how to not improve them. And some of my research was published in the Frag magazine. And in my spare time, I also used to be a member of the RESI project, one of the first framework for reverse engineering in the ELF binaries. Also this is a good time to thanks to Alexander, known as a solar designer, who always been supporting this project and actively challenging me during every step during the LKRG development work. Additionally, a special thanks to the following people for constructive criticism and brainstorming in the past stages of the project development, which is Rafał Wojtczuk, known as Nergal, Brad Spender, and Paxton. After such a long advertise, finally I can move to table of content. So what I'm going to talk about today. First, I will try to answer the question what LKRG is. And then I will try to present a threat model for Linux kernel from the LKRG point of view, because it's important for the project. Then I will move more to the more technical stuff, which might be boring for some of you, but I will try to discuss internals about exploit detection feature, some limitation of this feature. Then I maybe show you some demo if you have some time. Next, I will move to another feature, which is called runtime code integrity, which is also part of LKRG. Then I will speak a bit about communication channel. Then I will talk a bit about performance impact of this project for the entire system. And also I will discuss why LKRG is not implemented, apparently currently not, in the ring-1 in Hypervisor, but it doesn't mean it won't be in the future. And then I will speak about the future of this project, and in the end, maybe we have some time for question and discussions. So, okay, what is LKRG? So, apparently, the name is somehow self-explanatory because it's a Linux kernel runtime guard. So, it just guards Linux kernel during the runtime of the system. And this project is open source project, so it's published under GPL v2 license, so it's free. Everybody can use it, so please do, and send some feedback. And when I'm going to speak about LKRG, I always refer to the main branch of this project. And this main branch consists of 2 main features, which is exactly runtime code integrity, in short CI, and exploit detection, in short ED. And runtime code integrity detects, for now, just detects, in future also protects from the unsupported modification of the Linux kernel, and not only Linux kernel, also other critical resources in the system. And exploit detection feature will currently prevent Linux kernel exploitation process, at least try to do it. And there is also experimental branch, which is somehow independent of the main branch, which consists of from exactly the same feature as a main branch, but additionally they also have protected features, which has ability to hide and limit access to the critical resources like process, files, or logs, even to the root account, unauthorized root account. So if some attacker exploits some bugs in the system, in the way that he have a root shell, this kind of root shell with the correct configuration of the protected feature won't have access to every process in the system, because some of the processes will be protected even from the root account. Same with the files and some with the logs. So what about the threat model, which I mentioned before? When I was thinking about LKRG, at first I will need to think about what type of attacks against Linux kernel exists. And in short, I came up with the 3 buckets. First bucket is the attacking Linux kernel from the boot chain. So before Linux kernel even starts to execute any code, it can be attacked from the previous stage of the booting of the system and compromise the kernel security promises. Second type of the attacks, buckets of the attack, is somehow standard, and everybody knows it's just software vulnerabilities. Since Linux kernel is just a normal software, so we have vulnerabilities, so we can have exploit against this and compromise security promises of this software. And there is also a third type of the bucket of attack which doesn't really belongs to the first and second, because you can imagine that somehow system was compromised, doesn't need to be compromised from the boot chain attacks, doesn't need to be compromised from the kernel vulnerability attacks, but still system might be compromised because you can attach some vulnerable or malicious device which can have DMA access to the memory, and then at some random point of time, this privilege, like direct access to the memory, might change the kernel code pages. So even the vulnerability was not, there was no vulnerability exploited, there wasn't boot chain attacks, still the security promise of the kernel will be broken. And for example, some kernel backdoors will be injected to the memory. So from the LKRG point of view, first type of the attacks are currently out of scope. It doesn't mean it won't be in the future in scope, but just for current version is out of scope. Attacking kernel via kernel vulnerabilities is addressed by the exploit detection feature. And persistence of the attack is addressed by the runtime code integrity feature. And also, as I mentioned, there is experimental branch. And from the experimental branch, there is another promises of the project to be able to protect from the root account processes and files in the system and logs in the system. And that's why there is additional threat model points here. So from the experimental point of view, branch, you can attack any user mode process which is in the running state. And from the protected feature point of view, there was implemented protected process as a new feature to protect from the access from the root account to this process. But before process starting to execute, there is a file in the system which also can be corrupted. And this file also by attacker can be corrupted, and protected files was implemented to disallow even root accounts to have access to this file. Additionally, even if the file can be accessed in the normal way through the API, even the interprocess communication can be done in the normal way, root account, because it's a root account, still can attack the process and files via raw memory access or via raw disk access. And that's why LKRG virtually extends the functionality of the capsys raw I/O. Because capsys raw I/O never controls direct raw disk access, just raw memory access, LKRG changed the functionality of this capability and removed this capability from all of the processes, excluding the one which legit administrator wants to give it. And also, you can imagine that executable file also depends on the some shared libraries. So instead of attacking the process or attacking the file, you can still attack the shared library and inject your code in the protected process. That's why it's recommended this executable file to be compiled as a static binary and then enabled a protected file. And worth to mention that protected file is not designed just for executables. So you can imagine that you can lock down some specific configuration, like imagine OpenSSH configuration you don't want ever change anymore. You can enable protected file to the OpenSSH configuration file, and nobody ever will be able to change it, even the unauthorized root account. And from now, I won't going to refer anymore to the experimental branch. I will just always refer to the main branch. This was just a short note. This kind of feature also exists. So, OK, let's discuss a bit more about exploit detection feature. So the main aim of it is to detect kernel exploitation process by itself by detecting specific data corruption in the kernel. So it's not targeting any specific exploits. It's just trying to hunt of the exploitation process in progress. So obviously, the question is how it has been done. So current version of this feature maintains own task list in the system. And please make sure that it's written task, because task in the Linux kernel also refers to each individual thread as well as each individual process. So task is a structure who represents every thread in the system, including kernel threads too. And because LKRG maintains own task list and dump critical attributes, including like pointer value of the task structure itself, PID value, name of the process, pointer value for the credential structure, pointer value for the real credential structure, user ID, group ID, effective user ID, effective group ID, so on. Also, it's trying to maintain seccomp configuration for each individual task, which means that each individual thread in the process might have different seccomp configuration. And because of that, each thread has been independently tracked from the TIFF seccomp flag, seccomp filter, tflag, tsync, mode, what type of mode of the seccomp is applied to this task, and what filters, if they exist for this task, are applied. By doing that, apparently we have ability to detect if there is a token pointer swap attack at any random point of time. And for example, if the shellcode or ROP illegally call commit creds function in the random point of time, it will be able to detect that it happens and catch the exploitation process and kill it. The same by monitoring IDs, we are able to catch if someone trying to overwrite IDs in the memory and kill this process who trying to do it. By monitoring seccomp configuration, we are able to detect if someone tried to escape the sandbox based on the seccomp. And apparently, I've made a test, and each of these features somehow works, and I run the exploit again Chrome sandbox, the exploit who was using vulnerability in the wait T to escape the Chrome sandbox, and it's currently detecting the three ways. It detects the sandbox was compromised, it detects the ID was changed, and it detects the sandbox escape happens. Additionally, LKRG guards the following SE Linux variables, which is SE Linux enabled and SE Linux enforcing. And moreover, the following attributes is also tracked, but currently not used, but will be soon in the next version of the LKRG, which are secure bits, capabilities bits, pointer value to the real user ID subscription, and pointer value to the namespaces. And because of doing this, currently LKRG can still detect the SE Linux escapes, SE Linux disable attacks, and also it can, in the future, detect any kind of sandbox escape based on the capabilities sandbox. And by monitoring the namespace and user ID subscription, we are going to be able to detect container escapes and also namespace sandbox escapes, which will be added in the future in the LKRG. So also now the question is how the LKRG builds and maintains this task list and update logic attributes in the system and changes, because it happens all the time. So you can imagine that in the normal world, in the normal run of the system, you have multiple processes, and random process and random point of time might call some syscall. And if the syscall happened, LKRG intercepts kernel, and he overtakes the control at this stage before the even syscall starting to run. By doing that, LKRG have two ways of functionalities here. He can verify all of the task integrity in the system at this stage, not just for the one who calls the syscalls, but it will verify integrity of all of the tasks in the system now. And also he can inspect arguments which have been passed to this syscall. If LKRG finish the work or finish the validation of the task, it doesn't need to do this verification. It depends on the syscall, depends on the function which have been intercepted, but it might do it now. And then if it's finished the work, it allows kernel to normal continue the work. So kernel will call another function, it will call another function, etc. At some point, when the functionality of the kernel finished, it needs to return to the user mode, yes? And before return to the process happens, there is another hook by LKRG injected. And at this time, LKRG will inspect the return code of this function, who was just called in the kernel, to verify if the function succeeded or not, if the function failed or not, if the function, what the failure was and why it failed. And for example, if you call set user ID and it successfully changed the ID, then LKRG will update on database. And also at this point, another verification of all of the processes, not just the one who's calling the syscall, might be performed and verify of the integrity of all of the threads in the systems. And so the question is, what is intercepted? So these syscalls are intercepted. So set UID, set group ID, set effective user ID, etc., etc., etc. Set groups is intercepted. Fork is intercepted to be able to find out when the new thread or new process is created. execve and all of the group of execve is intercepted to be able to find out if process trying to overwrite our own virtual address layout and new database need to be updated. When the process dies or thread dies, we need to also know about that. And also from the integrity, runtime code integrity perspective, we also need to intercept init model and delete model, which I'm going to talk a bit more later about that. Also, there is a function may open, which is not open, it's slightly different function in the kernel, which is executed every time when any task wants to open any resources in the system. It's not only for the file, it's for any resource in the system. And whenever it is called, then the LKRG verifies if this specific task has access to this specific resource, or at least it should have access. If it has access but it shouldn't have access, it will kill this process or task. And also the important information is whenever all of this syscall is being called at any point of time, verification of all of the tasks will be performed, not just for the one who calls this syscall. Excluding the may open for the perf reason, in the may open will just verify the task who tried to open the resource. And this list is not closed, it probably evolve, but for now, this is how it is. So if you think about that, there is some limitation in this design, which we always were open about this limitation. So at first, it's bypassable by design, however, it can be defined. And the reason why, because it's very difficult to protect from the same trust level. If you want to protect ring 3, which is user mode, it's supposed to be done from the ring 0, from the kernel mode. If you protect kernel mode, the best way to do it is from the hypervisor, which is ring -1. But we're protecting ring 0 from the ring 0, so which is like cat and mouse game. That's why there is a two type of bypasses by design. First of all, you can fly under LKRG's radar. And second of all, you can attack LKRG itself and continue the normal work. So for the first bucket of attack, there is following one which is obviously to spot. So first of all, you can overwrite critical metadata, which is not guarded by LKRG, because you don't need to always have access to the full PowerShell, root shell, if you do attack, because maybe you just want to steal some memory data, just maybe want to leak the data, you don't overwrite anything. If you maybe just want to overwrite one special flag randomly in some random structure, which is not critical from the task perspective as an attribute, it's not guarded. So this is first type of attack. Second of all, it's a relatively early stage of the project, so maybe we forgot some interception. But if this happens, most likely you receive false positive, not bypass. Because if we cannot update the database, we'll think it's a corruption, so we kill the process. We haven't seen it, but still I cannot guarantee because it's too early stage of the project, but I still believe it's pretty solid. But I just put it because I should. And another attack is a race condition, because as I said, not every syscall is intercepted, just some of them. But so you can imagine that you can overwrite credential of the random task and then revert this credential as soon as possible to the original stage. So if you do it, you have race condition. But be aware, as I mentioned before, if the verification kicks in, it doesn't verify just the task who make a syscall, it verifies all of the tasks. So you can do, you are in the middle of the process of exploiting, yes, you update the privilege to some random process, and then, for example, random thread in the kernel dies. or random threads on the OpenSSH have been created, it will enforce validation of all of the threads. So your race here window is very small. Even if you do not use the syscall which are not intercepted, other components of the system still use them. And another attack, you can move entire kernel exploitation attack to the user mode, which means in the system there is already privileged processes, yes? You have like init process, which is always privileged. So instead of overwriting your own process, you can just inject some code in already privileged process to execute more data than it should. As a second bucket of the attack, which attacking LKRG by itself, there's also another type of attacks. There's another race condition problem, because you can try to corrupt LKRG's database itself and also attack the original attributes. But this is, as I said, again, a race condition, because you need to be as fast to do these two modifications before any verification routing will be executed, which again may happen in the random time in the system. But in theory it's possible. Also you can attack LKRG's internal synchronization on locking mechanism, but you need to be very, very precise of doing it. The reason why, because LKRG database is a red-black tree, which is self-balanced, which is always rotates in the memory. So that's why hunting this part of the memory which you're supposed to overwrite as a double overwrite is difficult. And also if you attack internal locking stage, it's not just exclusive for the LKRG, because these locks usually are also shared by other subcomponents of the kernel. So if you don't do it in the correct way or not precise and fast enough, you can just DOS the kernel. You can blue screen or you can just kill the kernel. You need to be very, very precise. And also, the last one, I don't think it's practical, but I should put it, that's why I put it. You can try to find all of the verification routines currently executing in the system and suspend them, and then trying to block creation of new one. It's very difficult to be done. I don't think it's a feasible attack. Other ones I think it's easier, but it also exists. And also, another problem of the LKRG is that there is some type of the kernel vulnerabilities which do not attack kernel, but attack user mode, even the vulnerabilities in the kernel. For example, dirty cow. It's very difficult to protect from the attacks like a dirty cow. You can still detect impact of the dirty cow. For example, if someone modify VDSO, then the runtime code integrity feature will detect that the VDSO was changed. But you don't need to attack VDSO using dirty cow. You can attack this kind of data in the user mode, which is not detectable. And I can show you a demo how exploit detection works. I hope I can. I don't know if it's feasible here or it's too small. Okay. Is it better? So at first I will try to run exploit for the UFO, which is UDP fragmentation offload, which was written much after I ever published LKRG. It was published recently, so it's a new exploit which I was not aware even exists. And LKRG will try to stop it. That's the CV number. So at first, that's my ID. I'm pi3 1000 user. I don't have access to this file, for example. Now, then I run this guy. I'm root. And I'm supposed to have no access to this file. Works. So now, let's try to run LKRG in the background. I run another shell. that's the logs. So now I will install LKRG, just install as a normal module installation. That's the log level. I don't want to spam with too many logs, so I put 0. You can see in the background that LKRG is successfully initialized, so it works. It's currently checking the system all the time. And now I will return to the original screen. I will make it smaller, that you can see in the logs how it works. I will try to rerun exactly the same exploit, and it's killed. I will try rerun it again, it's killed, and I don't have access to the file as I should. And if you see in the logs, exploit detection feature detect that this specific process with this specific PID, with this specific name, for example, change the credential structure. That's the address of the original one, the new one, and the new IDs. You can see the 1000 trying to be a 0. And then I will try again to disable LKRG, because you can do it. So it's disabled. I rerun the same exploit again, and it works again. So it works. So, yep, let's go forward. Let's speak a bit about runtime code integrity feature, which is another subcomponent of the project. So in theory, it's a very easy project because it's just trying to calculate a hash from the critical metadata or data of the system, and also gathers the critical CPU metadata, and the hash algorithm which is used is a SIB hash. But it's not as easy as it sounds, and apparently there is multiple other subcomponents of the system which is not related to the kernel, which are critical, which need to be monitored. And for example, any metadata of any core on a virtual CPU or any virtual core need to be independently tracked down. And currently we support x86 AMD 64 architecture, but it's a very modular project, so it's easy to add, for example, support for ARM, which maybe we'll add at some point. And LKRG sends something which is called Interprocess interrupt, now as EP, sends to each individual core in each individual CPU, forces to run exclusive routing, which is LKRG function. And this routing trying to guard the following data for each individual core, which is IDT entry, IDT entry point, and IDT size, IDT itself as a block of the data, and also all of the critical MSRs which are listed here. Additionally, LKRG tracks down information about how many virtual cores are, virtual CPUs and cores are available in the system, how many online cores are in the system, how many offline, and how many possible cores might ever be available in this specific system. And this was designed especially in this way because currently a lot of products similar of doing integrity of the system do not do it. So it's very easy just to put one random core in SMP machine to be offline, then again to be online, and this system doesn't track them down anymore. And then you just modify MSR, critical MSR for this specific core, to something malicious, and this system will not detect it. LKRG will catch this type of the attack because it has logic for hot plug in CPU and hot plug off of the CPU. Also the same with the virtual CPU, so you can imagine that if someone has access to the host machine and suspend the VM and add a new core, and then resume the machine, LKRG will be notified that this situation happened and will track down the newly hot plugged in CPU. Same with the physical CPU. Also, another guarded region by the LKRG is entire Linux kernel text section, which will cover almost entire kernel itself, like syscall tables, all of the procedures, all of the functions, all of the interrupt handlers. Also, Linux kernel have exception table, which not many people know, and it's also being protected by code integrity feature. Also, there is a read-only data section in the kernel, which is also protected. And optionally, also, it might protect IO-MMU table. By default, it's disabled because IO-MMU table might be dynamically changed by the drivers, legit drivers. But you can imagine that the administrator of the system knows that modification of the IO-MMU in his system should ever happen, because he might know which driver he runs and what the configuration is there. He might enable and enforce IO-MMU table configuration too. Additionally, each of the model of the system is also being guarded independently too. So the question is how this model is being tracked and discovered in the system. So first of all, each individual model is being found by tracking down the internal model linked list, and based on this information from the model linked list in the kernel, it will gather information like structure pointer to itself, which knows as this model, name of the model, pointer to the model core structure, and the structure itself too, size of the text section, and it also calculates the hash for the entire text section of the model itself. Independently, also LKRG will try to discover all of the models loaded in the system by gathering information called KObjects in the system. So Linux kernel have something called kset. Kset is a group of objects based on the type. And there is a type of model. Whenever you load the model is not only in the linked list, but there is a special KObject being created on the kset linked to the models. It's a bit complicated. So independently, also this following information also being gathered, like struct model pointer, like this model, pointer to the model KObject structure itself, and the structure itself, entire KObject structure, except of the list head and car reference information, since they are dynamic, also name of the model, pointer to the model core, and model core itself too, and also size of the text section and hash from the entire text section of this model too. And both of this information must match, even they are tracked down independently, but we know if the model exists, it's supposed to exist in two places, and if each of the information belongs to the two different places, each of them are still being tracked down individually. And also, additionally, what is interesting, the following information is tracked down, including how many numbers in the entire model linked list exist, how many numbers of KObject for the model exist in this specific kset, what is the specific order in the linked list in the model list, and what is the specific kset order in the kset for specific KObject. And I will show you why. Because it's how it looks like in the kernel. You have a linked list. You have pointer to model 1, to model 2, model n. And the same, there's different ksets for the different KObject, and there is also kset for the model KObject, which is somehow related to the linked list model. So if the attacker would like, for example, to hide his model, he will just create a different link in the linked list and disable this model. And at this stage, it will be very easy for LKRG to detect, because KObject exists, but model doesn't exist. But attacker can still, for example, create a new linked list in the KObject and also remove KObject. But at this stage, the order in the model list and more order in the KObject kset will change, because it's not the same as it used to be by normal development of the database. So it will detect LKRG that model starting to be hidden even existed before, because order is not the same. And also dynamic model loading can be disabled by the syscall interface. So you can completely lock down the kernel. It will not allow any more load dynamic models. Also, the question is when the runtime code integrity validation routine is executed. So as a standard way, there is a kernel timer interruption, which is generating a work item, which then is inserted to the something called shared work queue. It's not individual to LKRG. The reason why, because there is a special work queue in the system, which is used by multiple subcomponents in the kernel. So if you want to try to find out the validation routine in the kernel, which is LKRG validation routine, you will need to filter out on this shared work queue, because there will be 1,000 random tasks, not only mine. So there will be also other tasks, so if you just kill the work queue, you'll kill the system. So you need to filter it out. It's some kind of workaround mitigation, simple and cheap. Also, you can force validation of the LKRG dynamically by the syscontrol interface. Whenever any module activity is detected, so module being loaded or unloaded, it's also enforced validation of the code integrity. Whenever new virtual CPU or core is being added, for example, hot plug-in or hot plug-off, it will enforce validation of the system. And also on the very various random events in the system, which are unpredictable, to be able to remove predictability of the validation. And this is the list of the random events in the system with the different probabilities. So for example, if the random core become idle at any point of time in the system, there is a 0.005% of probability of validation of the integrity of the system. But some of the events always enforce validation, like for example, USB changes or global IC events probability will always be 100%. And some of them are random, so it's unpredicted to know when your validation will be additionally validated. And as I said, code integrity work is not so easy and not so pleasant as it sounds, because apparently there's a lot of caveats. One of them is something called jump label, which apparently enforces Linux kernel to be self-modifying code. And Linux kernel always modifies himself, which not many people know. It works like constantly changes on code. And this is apparently problematic, because if you calculate the hash, obviously the hash won't match anymore. So what happens if we detect the text section of the kernel was changed? We try to find out what's the offset where the modification were happened, and we use this offset to calculate the virtual address of this modified code. And if modification happened because of the jump label, there's only two possibilities what physical might happen. You might have injected something called long knob, or you might have injected something called relative jump instruction. And this if knob was modified to relative jump instruction, there is something that the destination of the instruction is still need to pointing inside of the same function or symbol name where the modification happened. So we have own internal decoder of the x86 instruction inside of the LKRG to trying to find out if it was relative jump instruction, and we validate what the target is, and the target is supposed to exactly point to the same symbol and range. And if yes, it's jump label modification. So other modification, which is also by jump label, the jump relative instruction can only be changed to the long knob instruction. And other modifications are banned, and more information you can find here, because there is some caveats, which it's too technical, which I don't want to cover here. Also, another things to mention, there is this situation happens only for the kernel core, not for the modules, but you can also, if you want, compile module with the same feature, and I will work on the next version of the LKRG to also support module to detect jump label modification. And also another problem, which I will try not to go to details since it's also technical. So Linux kernel, in short, in the SMP Linux machines, if you send an EP to the core, which is deadlocked, which might happen, there is an NMI watchdog which will kill not the deadlocked core, but it will kill the function who send an EP. And it's weird. But the reason why it's doing it, because if it's trying to kill deadlocked core, the system may be not stable. Because if you are able to send an EP, it means system is still stable. So if it kills that locked core, it might not be stable anymore, so that's why it kills you. Even your core, your function doesn't have bugs, in the logs you will see killed function. Looks like you have bugs in your code, but it's not. It's just the way how the Linux kernel works. So you can read more about that here. I published a blog post about that. So what about communication channel? Let's come back to something less technical. So LKRG exports syscontrol interface with these following options. You can, as I said before, you can completely block dynamic loading of the module by setting just this value to 1, block models equivalent 1, and none of the dynamic model will be loaded ever in the system. If you come back it to 0, you can still load a new model. It's very useful. For example, imagine the situation that you have random distribution kernel, like from the Ubuntu or whatever. There's a random also models installed on your system with the random implementation of the random stack. So for example, if you don't want to use SSTP stack, you can still have a model which is not loaded there. And if some user creates a socket to the SSTP connection, it will dynamically load the model to the system. If you don't want this to happen, you just make it to 1 and it will never happen. Also, LKRG will print a message, the system is clean. If you don't want to see this message because maybe it spams your log, you can make it to 0 and you will never see if the system is clean. But you still see if the system is corrupted. By default, this is enabled. Also, you can force validation by changing force run to 1. and then it will validate the integrity of the system, and will still revert this number to 0 that you can run it again. And also there's various log levels of the details between 0 to 4. 0 is non-log levels details, 4 is a lot of details, and there is also 2 debug levels, which is 5 and 6, which generate enormous amount of the details if you want, but it's not recommended. And also these random events of the system who forces validation of the system can be disabled by controlling this random event syscontrol interface. And the last one is a timestamp who controls how often the kernel timer generates interruption or validation of the routine. By default, it's 15 seconds. And what is the performance impact? We measure the John 1.8.0 Jumbo compilation with this specific flags listed here on the 8 cores system. And the numbers looks like this. So the fully hardened LKRG with all of the random events notification just add 2.5% of the performance impact. If you disable random events notification, it's less than 1%. It's just 0.7%, and still you have exploit detection feature and runtime code integrity by the timer, which is less than 1%, which is cool, I think. And now I think I have some time, I hope, to discuss why LKRG is not implemented in the hypervisor. So not many people realize that, but it doesn't matter where your assist is implemented. If it's in the ring 0, is it in the ring -1 like hypervisor, ring -2 like SMM, or ring -3 like AMT, still some of the problems remain the same. Doesn't matter where you are. For example, imagine you want to validate or read some memory page. You don't know what the state of the page is if you are not in the ring 0, because maybe kernel are in the middle of modifying this page. Maybe kernel just wants to page out this page. Maybe kernel wants to kill this page. You don't know. That's why you need to synchronize, regardless where you are, with the ring 0, where is the safe time to read this specific data. Regardless if you're in the ring -1 or ring 0, you still need to do it. Also, standardization of hypervisor world in the Linux is very underdeveloped comparing to other modern operation systems, at least for now. So, under which hypervisor your Linux box runs? Under KVM, under Zen, under VirtualBox, maybe you run some custom, maybe QEMU, I don't know. Which is not true in the closed platform. For example, you don't have the same problems in the other system. For example, Samsung developed Knox technology, which is similar because they know under which device they run, they know under which environments they run, they know under which system they run, under which configuration they run. So they always use trust zone because they know it is there. And they also know which trust zone exactly, which operation system in the trust zone exists, which they use. In the Linux, you don't know. In the Windows, if you have VSM enabled, you have warranty that under the hood there is always Hyper-V. So you have pre-assumption on the Hyper-V features, because you know it's always there. iOS have KPP, because it also knows which device they run, they know which environment they run, which configuration they run. In the Linux, we don't have this capability, unfortunately. And not all of the VPS solutions supports also nested virtualization, which is a serious limitation. So imagine you can buy a Linux VM in the random hosting. Some hosting doesn't even allow you to change the kernel. What about speaking nested virtualization? If it doesn't even allow you to change the kernel, you won't be able to use this feature, because now LKRG is just a module, you just install a module, and you have the same capability which I show you. And also ring -1 goes against mass deployment. So imagine you have farm of servers or farm of the VMs. So now what you can do, you can create a package, like a normal package, and install specific package on the thousands of the machines, and you have this feature enabled. If you have ring -1, you can't do this. And also, some of the servers are never going to be rebooted. They are not rebooted because their uptime is sometimes days, sometimes even years. So if the uptime of the server is a couple of years, how can you reboot this server and install some hypervisor feature? If you have LKRG, you just install the module, it works. But as I said, when Wild West of the ring -1 world becomes more unified in the Linux, it will be very easy to add ring -1 extension of LKRG, which will guard ring 0 instance. So we'll have exactly the same instance like now, and if the hypervisor become more unified, there will be extra module of LKRG, which will, from hypervisor, guard current LKRG in the ring 0. And it will solve the problem. So we'll have two modes of operation, weaker and stronger, depends if the hypervisor exists or not. But I still believe it's not the right time to do it now. And about the future of the project, from the runtime code integrity feature, I would like to cover more stuff, including APIC and local APIC. I would like to add the MADT table, FAT table, RSDT table, ACPI. I would like to also cover call gates, if of course possible in the system. And also I would like to check if the callbacks or notification routines which are registered in the system points to the module or to the core of the system which I know and I keep tracking down, not just to the random place in the memory. From the exploit detection feature, I would like to detect sandbox escapes based on the capabilities corruptions. I would like to add, as I said before, container escapes, which will be added for sure, same as a namespace sandbox escapes. And also, I will cover more kernel elevation of privilege techniques. And in general, I will probably work for better self-defense, like hash from the internal database and LKRG itself. Apparently, this segment is already done. And also, I will probably work at some time when I feel it's the right time on the Hypervisor extension to the ring-1 to guard LKRG from the Hypervisor, and probably much more, which I'm not aware now. So that's all. Questions and discussions.
Thanks. So, quick question because we have too less time. You've mentioned about adding support for capabilities changes or monitoring these. Do you also plan to add file capabilities modifications?
Yes.
Monitoring?
Every capability feature which exists in the system will be added.
Okay, thanks.
How do you know, for exploit detection, how do you know which threat or which process caused this activity, like modified kernel data, like modified privileges of processes or threads? On an SMP systems, there are many, or with preemptive kernel, there are many threads in the kernel mode at the same time. So if you only validate, check the integrity when the thread enters the kernel mode and leaves the kernel mode, there may be multiple threads in kernel mode at the same time. How do you know which one was malicious?
So validation routing works on these hooks works per code. So if any core randomly calls specific functions, there might be multiple validation routines assigned to each specific individual core. And even when it happens, depends on which validation we're talking about, because exploit detection features also rely on code integrity feature. So they might be random code integrity validation routing in the random core, just validating additionally the tasks itself. But whenever the syscall has been done with any core, there might be multiple cores doing validation at the same time with all of the tasks together. So that's why it happens quite often. And I've been doing a lot of attacks and trying to simulate attacks. Like, for example, I was creating tasks randomly, doing nothing for like a couple of hours. And then I was trying just precise at random point of time, having right primitive just to sweep the flag. But before any of the syscalls was returning, it was already cached, and the user mode process never have any chance to start executing because the kernel was blocking this level of returning to the user mode. So even they have a capability already maybe higher at some point of time before it returns to the user mode, to the attacker, a capability to execute anything, it was already killed.
I have one question. Well, a couple of questions, actually. By the way, really good project. And here.
Sorry, I don't see you. Okay, hi, thanks.
Really cool project. I have a question. I kind of skipped the beginning of the presentation. So first will be, is it in the mainstream kernel right now? And which version, if it is? If it's not, when do you plan to add it? Or when do you see the community adoption from the kernel community? And the second question is about the detection, actually. Can this module be used as a substitution to auditd, or maybe it's a supplement to auditd itself to increase visibility and in syscall monitoring?
So I saw community starting to produce own build of the kernel with this model inside. It's called VIP kernel, something like that, which I was not aware of before. I don't think it will ever be in the mainline of the kernel, but I don't know what people will decide. I will still develop this independently of whatever people will be saying or doing. I want this model to keep always updated. There is one thing which I didn't mention. I put a lot of efforts to support every various type of the kernel. So this kernel works since version 3.0 kernel up to 4.19, which is current, I believe. Plus, also I support variation, like Debian distribution kernel is supported, Red Hat supported. But if someone wants to add to the kernel, I don't have problem with that. And this model, I don't really get the second question. Did you ask if you can be replaced by comparing to the GA security patch or other patches?
Can you use this? The second question was, can you use this module since you can do kernel syscall detection and notifications? Can you use it as a substitution to audit D, and or as an addition to, I don't know, expand the visibility of the kernel syscalls?
I don't know what is OED, which you refer.
Audit D. The key audit, it's monitoring syscalls in systems.
Audit.
Yes.
Audit. Okay. Yeah, I think they're independent, they're compatible. You can use both. And apparently, I was also testing this with other LSM models. The only caveats which I found, the worst one, there was some crazy model doing crazy trick of modification. What you do, you just load my model after loading these crazy corruption models that they do. But with the audit, it's very compatible. There's no problem with that. That's far from my experience. And also, what is worth to mention that since a lot of kernel distribution do some crazy patches, also I saw some like Virtuoso distribution, which is based on the Red Hat, have some container models. I also haven't seen problem with that. It just works. Additionally, if someone doesn't want to use these crazy models, that's LKRG, I make a special effort to be able to make LKRG as a boot drive, as a boot model. So you can load this model before any other model as a first model is during init stage and still will work.
So does anyone else have a question?
I think there is one.
Thanks. I have a question. So for potential attacker, purely because of design, it is possible to detect and bypass this kernel guard system. So technically, it's possible. So for some skilled attacker, it's possible to modify all these existing CVE exploits and in such a way that these exploits are able to detect this kernel guard system, bypass the system, disable it, and they will run successfully. So my question is, how? So by design, this is possible. So my question is, how difficult is it to disable your system for potential attacker?
It's a very good question. Apparently, probably depends on the skills of the attacker. I was trying to do it. I don't know if I'm a good example, if it's possible or not, since I designed it and since I was trying to bypass it. I was able to do it with a lot of efforts, but I will need it to be very synchronized and precise. But I still believe that's why I still develop this project, that is give a lot of value. The reason why, because at first you need to be very good vulnerabilities to be able to do it. You need to have full read and full write primitive, and the problem is that not every vulnerabilities give you these possibilities. There's a lot of vulnerabilities doesn't even give you write primitive or read primitive. And this requires you at first that we need to have full read-write primitive, and then we can discuss about bypass, not before. There's type of the bugs like swap.js bugs, bad IRED bugs, sysred bugs, pop.ss bugs. They cannot give you read-write primitive, so this will always work. But if you have read-write primitive, yes, I believe it's possible.
The question of my colleague, and what about if you have just code execution primitive?
Sorry, can you repeat?
When you have just code execution, so you're able, you can choose which part of code you can run.
If you already have code execution, it's done, yes. Yeah. The problem is to achieve code execution.
Okay.
I was asking because, for example, in macOS, when they introduced system integrity protection, there was a very easy bypass when you just jumped to the code which disabled the system integrity protection. So, for example, if you have control over some pointer, and you can jump everywhere, and you have also info leak, so you know the addresses.
So you're talking, you already have ROP, which executes somewhere in the background.
Yes.
Yes, but this already requires you to probably have already read-write primitive somehow to be able to construct the full ROP chain we're starting to execute. But these guys will try also to protect you before you'll be able to do it. But if you do it, I believe you have a chance to do it, yes? That's why I put the slide. I was never defend that this is unbypassable project. Yes. Just my goal is that cost of developing it and making it in the high level is very, very high, and not every vulnerabilities give you these possibilities. But even imagine you have that. Imagine you have full read-write primitive. You control everything. As I said, you have race condition problems. You might be not fast enough. Maybe you run 50% of time you succeed, 50% of time you crash the system. Or maybe 20% of time. That's why I was putting a lot of efforts for unpredictability when the validation has been done. That's why you have random events on the system who does validation. But as I said, I never defend it as unbypassable. It's bypassable by design. But the cost of bypass is very high.
Okay, thanks for all questions. And also thank you, Adam, for your great presentation.